So it's my pleasure to introduce our first speaker, Timur Bazhirov from Matra.com, and he'll tell us about data standards.
Thank you, Francesca. Thank you for having me today. Thank you for waking up early, coming up to this presentation. Today, I'll tell you about how we built data standards at Matra.com. And if you remember nothing from this presentation, then these are the summary points. It's right there for you. We are a digital ecosystem that helps material scientists utilize digital approaches like density functional theory, molecular dynamics in a more collaborative and a more accessible way. And we focus on democratizing digital approaches that are developed by a community, not by us. We have over 10,000 users today, and we have dozens of enterprise clients, including the Air Force Research Lab, Merck, Shell, Toshiba, among many others. And it's not by design, but by the virtue of requiring it, we arrived at the data standards framework that we believe could be useful to the rest of the community. And that's what I'm going to be speaking about. If you think about potential collaboration, let's talk later today or between 5 and 6. We are thinking about an impromptu, unofficial happy hour. If you're still around during that time, let's talk. A little bit about myself. I was born and raised in Russia, came to the United States in 2008 to work on my PhD at UC Berkeley. And I was always surrounded there by people who are very smart, working on important problems in material science. But we ended up using code that was written back in 1977 and really wasn't really easy by any means to deal with. That's why I got started something that was called exabyte.io. In 2022, we got rebranded as Matera.com. Here you can see a snapshot of the Wall Street Journal that covered our seed funding round. And fast forward to where we are today. We are called Matera, which stands for the era of digital materials engineering. And that's why we have a digit in the name. Really what we represent is a big transition to AI-driven materials R&D, where we used to have experiments and theory and then computations. And today we have a lot of data that's produced by all of this. So we need new types of digital tools to be able to deal with all this information. And Matera is one of them. We sit right in between the three domains that are involved in AI-driven materials R&D, which are material science itself, data science, and computer science. These three are very, very different from each other. But in order to harness AI, we have to work right at the intersection of those three. And we exist to build the bridges. So you can think about our approach as the one depicted here. Materials R&D Cloud, where cloud stands for the focal point where many types of scientists, computational scientists, experimental scientists, data scientists can come together, send their data to the point where all of them interact. It can be private cloud, it can be public cloud, it can be on-premises server. It doesn't matter. What matters is that that's where all these parties interact. We believe that it's possible to put any multi-scale modeling tools, feed them into this platform, make them work for computational sciences, for experimental scientists as well. And then it's possible to gain analytics from this platform for the R&D management to get their metrics and make sure that they're spending the dollars correctly. Here is the figures about my company. We have $3.8 million in funding, including the likes of Peter Thiel and Tim Draper. We have worked with three of the largest funding agencies, Department of Defense through FWorks, Air Force Ventures, Department of Energy, Department of Commerce as of lately. We have presence in Japan and India. And we have over 10,000 scientists that registered in our platform as of today, executing hundreds of simulations, just extracting value, extracting information about tens of thousands of materials. You can see some of the customers that we work with on this slide. Includes, as I said, US Air Force, Shell, Merck, DOE labs, and many other institutions, as you can see. What we do is we bring together the perspective of an academic institution where they are focused on fundamental science, and large enterprises that are focused largely on applied research, something that can be applied tomorrow, so versus something that is very fundamental and basic. Usually at the academic institutions, the work would be non-commercial, and we help commercialize this work. We help take it to the level where it can provide some specific insights to large companies when they're building their products. For example, they could be asking questions like this: how do we build a 10% better battery within the next, whatever, 3 months time frame? I'm just making numbers here. But academic institutions could be asking questions about how do we build a JSON categorization of battery materials? A very fundamental question, two are completely different, right? But if we now use this framework to screen 1.5 billion battery materials, and then we try to find the ones that actually satisfy the requirements for this large enterprise, that's how we build the bridges. That's how we make a statement that both sides can work with. Okay, let me give you an example of how the platform actually looks like, what we can do. We believe that all parts of the R&D lifecycle should be there at your fingertips when you open the browser and you type Matera.com, which means that you should be able to design materials, design modeling workflows, run simulations, analyze the data, and build analytics and artificial intelligence right there at your fingertips in the browser within a couple of clicks, as easy as possible. So there we go. Okay, let me try one more time. Maybe it's gonna work here. All right, we're gonna have to do that. So here is a demonstration of how the product works today. So what we could start with is users creating new materials, right? So they will come into a browser, open Matera.com, create a structure, which in this case is like aluminum gallium arsenide surface. They could create multiple structures for a notched elastic band calculation. Like in this case, we'll have a chemical reaction that is depicted in particular postcard files. And then they would select properties that they're interested in studying. And here's a list of workflows that we have templated for them: electronic band structure, phonon calculations, optical properties, mechanical properties, anything that we could extract, we prepackaged and templated here so that people who are just starting with us, they can click on one of them and click select. Next step is selecting the infrastructure. We work with Microsoft Azure, with Amazon Web Services, with Google Cloud. And we also work with on-premises solutions, work in progress still. But the idea is that people can select which system they can send it to do the calculations. And then as our system tracks the progress, the calculation gets executed, everything is green, everything is done. And at the end of that, people get a result like this. So a band structure plot, or density of states plot, or chemical reaction plot, something that they can analyze. Now, what's under the hood? Let me try and get to the next slide. Give me 1 second here. Under the hood, we have a system that deals with data that is produced by users, by actors in our platform. And here is a probably overcomplicated diagram for 9 o'clock in the morning, but it explains what's happening, right? Users come into our web interface, they create structures that we store in a database as JSON. The same thing happens for simulation workflows. So workflows are represented in static, searchable, declarative JSON structures, and we store them in a database as well. And then we apply workflows to materials, maybe in a high throughput manner, maybe in a one-off manner, and then we send it back to the database, farm it out to the cloud. We assemble the computational infrastructure in the cloud, and as the calculation is running, we extract properties, we store them back in the database. So database is really the key focal point here where everything happens, and then we show the results to the users. Now, I'd like to focus more on how we actually built the standards and what's being stored in a database based on our discussion yesterday that the data standards are important. So our approach is inherently open. There is a large open source component, and we start with developing standards for storing all this information inside our system. And when we deal with native applications, things like WASP or Quantum Espresso, we have to also write extractors, which will take information in the native format for WASP and then convert it to the data standards so that the applications that can create a defect in a structure, that can create a surface or manipulate information in some way, they can work with this data. And all of this are open source. Then we start crossing the border here into the Matera platform. So we take the open source component, we integrate it into the platform, and we make it available for different types of the platform users. Here we have computational scientists, experimental scientists, data scientists. Obviously, our main focus today is on the computational scientists, because that's where our expertise and our background is from, but we have support for and envision design support for other types of activities too. And then the third portion here is inclusive design for new types of applications, compute, and data, meaning that if we have an institution that have their own computational clusters or their own cloud-based systems, we should be able to incorporate them into the larger platform and put them together to work with other players. Now, to be able to facilitate something like that, we have to build data standards. And the number one point on building, on the path of building data standards, is ontology. Here we have a picture where material, job, and workflow and model are the entities that we have to deal with. And there are certain relationships between them. For example, material coming together with a workflow represent a job. And when the job is done, it generates a property which has a certain precision associated with it. And the workflow has certain units that are executed in a particular logical progression. It also has a model. A model can be subdivided into unit models. For example, if we have a complex calculation like GW in density functional theory, then there are multiple steps involved, including basic GGA-based or LDA-based self-consistent calculation, and after that there is many-body theory. So understanding what's inside is what we're trying to achieve. Then we have different types of entities. So this is a snapshot of the entities that we deal with in our solution. We start with logical workflows that are being executed inside our platform. And those are subdivided into smaller units, and then the context providers that allow people to preset settings for the workflow. So not specific keys for WASP or Quantum Espresso based on material information. And then Quantum Espresso or WASP or LAMPS or anything else would be called an application. Application can have executable flavors, templates. Without going into the details, this just has a snapshot of all the players, all the entities that are involved in our landscape. And for those of you who think about this as too computationally inclined, many of these items can be generalized to be able to deal with experimental equipment, because there's still a workflow that we apply when we deal with experimental equipment. So the concept itself can be generalized. And then we also have to deal with the types of users. So there are computational scientists, there are experimental scientists, there are data scientists, there are application developers, so people who develop new applications. And then we also have a concept of curation, where we have regular users that just contribute to data, and curators, the people who can understand whether or not the data is good and rated. The second point in building data standards is categorization. When we deal with the large zoo of different models in density functional theory, we have to understand what is it that we're exactly dealing with and how to make it searchable. So we published a paper a couple of years ago explaining the concept. All of this is still work in progress, and none of this is perfect, but we have a concept where we try to categorize the models that we deal with. For example, when we speak about density functional theory, it will be under physics-based quantum mechanical density functional theory ladder of this categorization. And then if you use spin-orbit coupling, we'll apply a tag spin-orbit coupling here. If you use relativistic pseudopotentials, we apply specific tags here. So then we can search for it when we get the results. I know it's hard to see it, and it's early in the morning, but just bear with me here. We have categorization work in progress. Early on, categorization for materials and properties that we deal with. So for materials, we have categorization by different domains. So it could be semiconductor, solar material, polymers, and so on. For dimensionality, we start with 0D, 1D, 2D, 3D, and so on. We have electrical conductivity-based categorization. For properties that we extract, we have different domains, again, attached to those properties so that we can search through them. And step number 3 in building data standards is defining how the data is stored in a database. So schemas, database schemas, and we have a set of examples accordingly to follow. So on the left, probably incomprehensible and hard to see portion of it, but it's available on our GitHub. Is an example representation of a material where we can see that the material structure will have a crystal basis. It has a unit cell formula which are defined here as strings. And then on the right, we have an example data structure which represents a material. This is silicon FCC adhering to this particular schema. So we know that when we ingest the data into the database, it is of a certain type and adheres to a certain schema, and we can stand by. Here is an example of our recent work with NIST, where we created schemas for NIST Jarvis. And this is how we can start building back and forth conversion between different formats. So in this case, we have Jarvis database entry schema, which contains certain keys and descriptions of those keys. And that's where we believe AI could be helpful by writing automatic conversion between one format and another. So things like ChatGPT could probably spit out the code base based on the schema definitions pretty easily already today. Now, the next level here is how do we enable community contributions? So once we have data standards, once we understand what goes into our database, how do you enable people to create new data? And we believe that we have to start with templated items, templated workflows. So we pre-initiate our database with templated workflows, and we separate those workflows into building blocks or Lego blocks, as we call them. So every workflow is built out of sub-workflows. For example, if you want to run a plane wave self-consistent field calculation, that's a sub-workflow. That's present in many other workflows. If you use do GW, we still have to do self-consistent field calculation first, and we can reuse that Lego block. On the right, you can see the user interface where all these different types of Lego blocks are summarized and are accessible for our platform users to quickly select. And then there is the logic that will change the input file for Quantum Espresso accordingly based on the type of materials that people select. And then the second portion here to enable community contributions is to enable custom applications and custom workflows. Custom meaning that if we don't support something today, we can work with developers of a particular code to help and integrate this solution. So if you're developing a solution, you're a code-based developer, a software developer, then there is an integration client that we can integration process that we can work on together to create a workflow, an application in the system to which other scientific community users of our platform can navigate and search and then apply and then deploy in a more accessible, easier to use manner in our system. All right. Just to summarize, I'll give you a use case of how this is actually looking in our platform today. There are multiple different types of case studies we had. I'll focus on one of them, semiconductor electronic materials heterostructures. And here is the valence band offset calculation. We start with a heterostructure, moly sulfide, tungsten sulfide. This is the snapshot of the workflow, which has multiple different steps in the system. And then we would come in to select that workflow in the user interface. We'll select the interface components. We tweak the parameters if needed. And then as I'm running out of time, the job miraculously gets submitted and gets done, and we get the results for it. And all of this is organized and searchable. All right, without taking any more time, this is the summary. You can read it. I'll take the questions. Thank you.
Thank you very much. Any questions?
It's not going to be. It's going to be when you is that working? Yeah. On the tags and the properties, your semantic ontology structure, you had materials on one side and calculations on the other, and then properties on the third. Right. So my question is, if you start doing calculations on derived properties, do you have an indirect link between those?
Right. I guess you're hinting at the fact that it's not easy to completely decouple those, and materials have properties, and some of them can be there before calculation, some of them can be derived after calculation. So properties are the gray area where I think we sort of connect the two, and that's where community input will be very helpful to figure out the specific structure and then stick to it.
Sometimes they're derived, sometimes they're original.
Absolutely.
So you mentioned that you connect to a couple different cloud compute providers, and I was
correct.
wondering if you also support deploying into an HPC environment that might not connect well to the external world.
Yes, absolutely. That's a very common use case. We're working with Berkeley Lab on that, and we'll be open to working with other people as well. The only concern is that most of the cloud providers there are interchangeable. So the development work that we have to do on our end to cover cloud providers is pretty much the same as we cover one of them. And many HPC systems are kind of one-off. They have specific routines, but we'll be happy to discuss.
Any more questions? Just really quickly, when you talk about data standards, do you actually talk also to the various organizations that have working groups on developing this? Because it's such an important field that to do it, getting into the same format altogether.
We talk to NIST. But I think not many other organizations understand the importance of data standards. We yesterday at the panel, it was a sort of a revelation that many people I think that they're important. Most of the time they think about applications, right? How do we apply a particular simulation for a particular purpose? But it turns out that unless we focus on data standards, it's going to be very hard to build something coherent and sustainable over time.
Yeah, that's the coherence exactly that concerns me. And I don't know, for example, there is the Material Research Data Alliance. They have a lot of working groups on data. Just wanted to know the connections or path to grow it together.
I'd be glad to discuss.
Okay, thank you very much. So let's thank our speaker and